So now let's talk about phase changes. So phase changes are just going to be how different phases exist at different pressures and temperatures. So as you can imagine, if I just took one single pressure and I just dragged it along, it's not very easy for me to say, oh, it's going to exist in just this one phase. Low temperature or low pressure means, hey, it's a liquid, solid, or gas. It doesn't work that way. Same thing with temperature. Even if I try to drag it right here, I'm still existing in this phase as well as this phase. So, as you could imagine, what exists at a low temperature and a low pressure? Well, when we talk about low temperature, what do you usually see at low temperatures? Let's say we're talking about water here. This would be a solid. And then what exists at low pressures and high temperatures? A gas. And then what exists in between? Liquids. So, now that we know that, let's say now what happens as we increase or change the pressure and temperature. Well, every single one of these lines represents a boundary between two different phases. And so there are a few that you already know guaranteed. So if I move from a solid into a liquid, I am melting. Doing the reverse would be freezing. As a liquid moves into a gas, I am evaporating. And as a gas moves into a liquid, I am condensing. And just so we recall, we want to lower the energy of a molecule if we want to get it to convert from a gas, which is high energy, high speed, down into a liquid, medium speed, medium energy, and then even further reduce the temperature and thus the energy into a solid, which is basically the lowest energy and lowest free movement. And just remember that the temperature is directly proportional to the kinetic energy for molecules. So there's two that we left off here. We left off solids to gases and gases to solids. And I always hated trying to remember these as well, just because sublimation, deposition, which is which. Remember, solids sublime. So as a solid moves to a gas, that is sublimation. And the reverse, a gas moving into a solid, is deposition. I never remember deposition, but I know it's always between deposition and sublimation. If you know that solids sublime, it's pretty straightforward. Now this point here is the triple point. And that's where a substance can exist as a solid, liquid, and a gas simultaneously. There's some great YouTube videos showing this process. I really encourage you to go look at it. And the last position I would just want to mention real fast is this point. So this is the critical point. The critical point is a high yield thing to know just because it is the point at which the liquid phase and the gaseous phase of a substance are basically indistinguishable. So at this point, there's there's the pressure and temperature that exist at the critical point. And if you mapped out what the actual position was, so let's say going this way, right here would be my critical pressure. And then down here, well, that's a little bit off. You get the point. This would be my critical temperature. And so remember that this is all about getting those intermolecular attractions to happen or not to happen. And just as a example, the condensation that you see in your drinks is because of one of these processes. So it only happens on cold drinks, right? Well, the reason is if I have a cold drink, well, that water or whatever's in that drink has very low energy. And that low energy liquid starts to make the walls of the container very cold and very low energy. So as gas particles start to move around, they'll start to feel that low energy point, and because it's low energy, and that is going to mean that they, it's low temperature, and so because it's low temperature, it becomes low kinetic energy, those gas molecules are going to start to slow down. And as they slow down due to the low temperature, they're going to be around the water molecules or other molecules that are along this wall long enough for them to form intermolecular attractions. So it's not like you have the liquid inside of the glass that's escaping and somehow getting to the outside. You're just having such a low energy point in a room that when gas molecules get near it, they themselves are going to enter the liquid phase because you're reducing their kinetic energy enough for them to be around other molecules enough to form intermolecular bonds. And so remember, it's not covalent bonds, it's not H2O with an oxygen and then its hydrogen breaking and then somehow leaving as like an OH or just an oxygen. It's one H2O molecule encountering another H2O molecule, and the hydrogens of one oxygen are slightly attracted to the oxygen in the other H2O molecule. An example of that would just be, I'll just draw it real fast. Here's one H, or there's one oxygen, there's the two hydrogens. Another oxygen with its own hydrogens kind of sees that positive hydrogen and starts to kind of feel a little bit attracted to it. And so if they get close enough, they can start to form these bonds and hold each other near enough that they can enter a liquid phase. Now we get into phase diagrams. And phase diagrams, relatively low yield, just because the two main topics that you see, the heat of fusion and heat of vaporization, can easily be calculated without knowing very much information at all. So why is that? Well, let's see what's actually happening. So at this point here, let's say this is point A, it's at -40 degrees, and this is for water. Well, at this low temperature point, it's existing as a solid, no real issue there. But I can start to add heat to this, and the formula would just be the heat added has to be equal to MC delta T. As I increase the temperature by adding heat, I can get to 0 degrees Celsius, the melting temperature. But I can't just turn a solid into a liquid as soon as I get to 0 degrees. Something has to happen, and that something is I need to break those really strong intermolecular attractions between all the different molecules that are in the lattice structure of the solid. And so that is what we call the heat of fusion. The heat that I need to put in to take a solid, break some of those intermolecular attractions to get to a liquid. And so for water, the heat of fusion is equal to 334 joules per gram. So if I had 10 grams of water, I need to add in 3,340 joules of energy just to convert it. And that is just energy that is going into this conversion, not into raising the temperature. As you can see, this temperature does not increase during the heat of fusion. So now once I actually take my solid at 0 degrees, convert it to a liquid at 0 degrees, I can start the extensive process of heating up that liquid. Again, because there's no phase change here, all I'm going to do is supply temperature. I just want to supply temperature, supply heat by increasing the temperature. And that temperature is just to get those individual molecules excited enough and high energy enough to the point that they can actually escape the liquid as a gaseous molecule. So from 0 degrees to 100 degrees, I am just increasing the temperature by adding heat to excite those liquid molecules. They still have some of those intermolecular attractions that the solid had, just not as many. But when we get to delta H vap, or the heat of vaporization, so at the heat of vaporization, this is where we need to actually add a lot of energy. We're not just trying to break some of the bonds, of the intermolecular bonds. We are now trying to break all of the bonds. We need to take one of those H2O molecules and completely rip it out of the solution. So to do that, how much energy do we actually need to supply? Well, the heat of vaporization for H2O is 2,260 joules per gram. So if I had 10 grams of water, the energy I need at 100 degrees to change that liquid into a gas is 22,600. So now that I do that, and this is at the liquid gas barrier, liquid solid, liquid gas, now I'm actually a gas at 100 degrees Celsius. So just now I can freely heat this gas upwards. And as I do that, it's just MC delta T. And that is basically it. Now let's just do some quick practice problems. Which of the following is an example of an amorphous solid? So loosely packed solid. Not diamond, not quartz, not table salt, it's glass. Consider the phase diagram for carbon dioxide. At 0 degrees Celsius and 5.11 atmospheres, what phase does CO2 exist as? Well, 0 degrees. Oh, I don't know where 0 degrees is. Doesn't matter. If I know this is 5.11, and here is my boundary, that means that some point along this line, that is 0 degrees Celsius. So if I know that this is the solid, this is the liquid, this is the gas, CO2 exists as a gas. The arrow on the graph represents what kind of phase transition? Okay, solid to liquid. Cool. One thing I forgot to mention. So we know the critical point, right? This is the point that a gas and its liquid are pretty indistinguishable. What happens if we take the pressure or the temperature above this point? So if we move anywhere into here, we exist as a supercritical fluid.